Hi guys, so this is the second video for today and we're going to talk about parsing of AST tokens. Sorry about that. So anyway, so we have written some pretty simple macros right now. Like we have like the most trivial macro in the world, which is this comment thing here. And we have this slightly more complicated macro, which is the piping one, but it's still very simple. I mean, I just have to handle the case of what happens when it's empty and what happens when there is at least one value and possible list of other AST tokens. But of course, you know, there are many tokens that are much more complicated. Like for instance, the definition of this do macro is much more complicated than that. The definition of the def macro is also more complicated than that. You know, the definition of the def macro is also more complicated than that. So how do you work with that? Well, initially it was kind of hard. Like for instance, if you remember from when we looked at the quoting macros in here, you know, these are pretty primitive, pretty early on in the development of the standard library. I basically made them because, you know, I just couldn't keep working with syntax, you know, directly. It was just too annoying. But as you can see, you know, I am working with AST tokens also by doing pattern matching on them. This looks case might look weird. This is simply the primitive way of doing pattern matching in looks. So the case macro here actually compiles down to the looks case special form, which does not support many of the features that case does. But anyhow, so you know, at this stage, I am doing pattern matching on everything, which is really annoying. Like for instance, in this onTemplate function that I use in my template macros, as you can see, I am working directly against the AST tokens, parsing directly. It's so annoying, so much code that has to be written, and it looks really ugly. And it's also there's also a problem that it's very hard to work with complex inputs. Like for instance, let's see if I can find the definition of this def macro. Oh, here it is. Just check out the pattern matching that I need to do against the inputs. It's insane. I have to pattern match against each individual list element, and I have to check the kind of element it is and its contents. And you know, what happens if there is an export keyword, what happens if there isn't, what happens if someone gives it a name, a raw name, or a form name, or what happens if someone puts a type or misses type. You know, there's a lot of things here that could go wrong, and I need to handle each particular combination of inputs in a different branch, because at this point in the standard library I do not have the tools to make writing complex macros easy. I don't have them. It's too early. It's like this is located at the, you know, after the first 1200 lines of the standard library in its entirety. There's nothing more here, so it's incredibly early on. As you can see, it's very annoying to work with this. So, oh, by the way, I forgot yesterday. I forgot to mention what idents are. So an ident is basically the ident type of that you have, for instance, in symbols and tags in our AST tokens. It's basically just a two-tuple of text. Oops. The first one is the prefix. The second one is the name. They're used for referring to identifiers or variables or the names of tags also. Here you can see some of that. Here's a function that if you give me an ident, I'm going to give you back a symbol AST token containing that ident. You know, at this point, like I said, it's very early on in the standard library. I don't even have the templating macros, so everything has to be generated in a more primitive and annoying way. It's really ugly. It's not nice. Now, in terms of generating the code, things have gotten much better because of the templating macros that we now have. But things have not just gotten better in the standard library when it comes to generating the code, but also when it comes to reading the code. Now, I previously showed you the example of of defining that def prime macro. That was pretty ugly. I had to do very direct parsing, and I had to handle all the different possibilities of inputs directly, and it was really ugly. And even for this piping macro, I kind of have to do pattern matching too. I mean, I have to do pattern matching against the tokens to figure out whether they are empty or contain at least one element. I'm still doing pattern matching, and this is very simple because I'm just finding things directly. I'm not exploring how the contents look like. But if I were doing so, it would look very similar to that definition that we saw, which was ugly. Well, what happens when you want to do something more complex? Do you have to do that? Well, not anymore. There's a better way now in the standard library, and there has been for a while. Pretty much like since the first few releases, maybe the second one or even the first one. I don't remember well. It was too long ago. But that feature has been here for quite a while. And I think I wrote it in one of the blog posts in the Lux devlog, but maybe I didn't touch on it. Maybe I didn't talk about it too deeply. I don't remember well. So we're going to talk about it here. And, we're going to talk about it anyway. So there is another way of defining macros in Lux. Okay? And we're going to use it and explore it by making our own def macro. Yeah, you heard it right. From now on, we will stop depending on the def macro that comes from the standard library, and we will make our own. Which, of course, we have to do over here as the first thing, because otherwise the rest of the code is not going to see it. So we're going to define it here. So basically, what we have is I think I've gotten carried away with this. So basically, we're going to be using a new way of defining macros. So we have already seen the base way, which is def macro, which, by the way, I never use. I only ever use it in the standard in the Lux module of the standard library, because the other form is not there yet. But I don't use it like for writing my own code anymore, because def macro forces you to do pattern matching, and that's annoying. Instead, I use a better one. And we're going to be importing, we have already seen this meta module, right? Well, it turns out there are submodules of this one, and we're going to be using the syntax module. And syntax gives us the defsyntax macro. Pretty sweet, huh? So defsyntax works on the idea of syntax parsers, which are monad-based parsers. So basically, they can handle the state of a parsing session, which is basically the list of AST tokens that you have yet to process. And the idea is that you parse the inputs of a macro in a more intelligent and useful way than having to do raw pattern matching. And then with the values and the information you get from that, you generate your code. It's pretty simple. It is very, very, very nice. So we're going to define our own version of definition, and we're going to have to take a declaration, which we're going to be using. We're going to be getting from a def declaration parser. This caret here is not essential. It's just part of the name. It's not like any special syntax. It's just that whenever I make syntax parsers, I like to put a caret at the end of the name to be able to quickly identify them if I see them. Now this function here has not been defined. It doesn't exist in the standard library, so we are going to be defining it. But the point is, that I can use it to get a declaration, which is basically, this here. This factorial n thing is the declaration of the factorial function. This here is the declaration of the power function. This declaration of the least iterate function, so on and so forth. So we're going to have a declaration. We're also going to have a type, which is just going to be an AST token. And when you don't do any kind of special or complex parsing, you don't need to put anything within these brackets, because these brackets basically mean this is going to be an input to to my macro, and this is gonna be the parser who gets the input. But if you just put the name of the input itself, it just assumes that it's gonna take one token from the inputs, and that's it. There's not gonna be any kind of complex parsing involved. So we're gonna have the declaration, we're gonna get a type, and we're gonna get the value, which is another simple AST. In this case, in the case of factorial, this will be the type, this will be the value, and of course, this will be the declaration. And then we're gonna do something with that code. So, you know, how does this declaration thing work, and how does do these parsers work? Well, remember how I showed you that, you know, that there are these macro and looks types that are monadic in nature, and, you know, in the case of looks, you know, it wraps a value within a computation that does something with the state of the compiler. You know, like I told you that you know, different functors and different monads have different superpowers, right? They have different powers, and each, you know, the looks monad gives you the power. The looks functor gives you the power of being able to produce values through computations on the state of the compiler. Well, there is a type for the parsers. Here it is. Looks a little bit weird. Sorry about this part of the documentation. Let's remove it, and what we end up is this. And this actually looks very similar to this looks type over here, right? So instead of compiler, we have list of ASTs. That's going to be the state that our parser is going to handle. And this error type here, this error type is just equivalent to either text. So it's basically the same thing. We have just used the same thing. So, you know, in this form you can see it's basically like the looks type, but it uses a list of ASTs as the information that it works with instead of compiler state. And pretty simple, huh? Give me just a moment. I'm gonna go pick up the phone. Sorry about that. I was picking the phone. Anyhow, back to this. So let's make our parsers, right? So we get many parsers here from the defsyntax module, and, you know, let's make a parser, right? Let's make this parser here. So there are two ways in which we can make a declaration. It can be a simple declaration, which is just a name, you know, the name of our constant value that we're generating, or we can make a function declaration, which basically has the name of the function and the ASTs of the values. Right, and we're not going to just take names because, for instance, the power function we are receiving a tuple syntax, so it's not just a name. So this is what we're going to be generating with our declaration parser. So basically, I'm going to be doing this. You know, I have some combinators, which are functions that are used to create parsers, bigger parsers out of smaller parsers. So we're gonna have this combinator that, you know, if you give me a symbol with a prefix, this parser produces the name of the symbol. So for instance, if you give me the symbol factorial that has no prefix, you will get a text that says factorial, which is the name of the definition. And alternatively, if you give me a form that contains a local symbol and 0 or more ASTs, you know, this is the identity parser. It just takes a token and gives it back to you just like that. Which, by the way, is what this turns into. These two things are basically just this, just in a more convenient packaging. So if you give me, so with these two parsers, I can parse the declaration. Now this looks very weird. This looks very weird. Like what the hell? Like, how does it even work? I mean, yeah, I get it. You know, local symbol, yeah, symbol with a prefix, you get the name of the symbol. This form thing, well, basically it says, hey, if you give me a form, I'm gonna use the parser inside to parse the contents of the form. Simple as that. This and here basically says, hey, I'm gonna be running these two parsers one after another. So, you know, I'm gonna look for one symbol and then an arbitrary amount of AST tokens. It's very simple. But why does this work? Well, this kind of works like this. It basically says, hey, this pipe caret parser basically says, you know, for all types A and B, you know, if you give me a parser of A and a parser of B, then I'm gonna give you back a parser of A or B. And this is the way, this is a macro for building sum types. Remember sum types? That's what you use for making variants. Well, remember when I told you that types in looks are structural in nature instead of nominal? Well, that means I can just use this combinator that works with arbitrary sum types to make a parser for a particular sum type, which is this. Because this particular sum type expects a text on the left side and a tuple of text and list of ASTs on the right side. And that's what you get. A text on the left side and a tuple of text and list of ASTs on the right side. So using these combinators that are generic and can be used for anything, you know, I can make a parser for my total value. Now this is one of the really cool things that you can do by having structural types, which is something that you cannot do in other programming languages. I cannot stress that enough. You cannot do it. I mean, yeah, you can kind of hack it and kind of force things in, for instance, Scala with Scala C and maybe some weird obscure Haskell library, but they're not features that those languages really give you, like the languages themselves. But looks actually does give you that, because looks types are structural in nature. Big departure from types in most languages. So hey, we have our parser here. We have a parser for our declaration, and we have the type, which is an AST, and we have the value. So how can we make our syntax here? Well, by the way, I said that parsers in the looks library are monadic in nature, and they are. But right here, we're not doing any do syntax. We're not explicitly using any monad. The reason is that these combinators for the parsers actually do it for you, so you can just use them and avoid having to do the monadic parsing yourself, which is very comfortable for a lot of scenarios. Sometimes you do need to enter the monad, which is called the parser monad, but it's not that big of a deal. You don't need to do that much work. But you know, this it's really nice, because this defsyntax declaration here actually does use the monad behind the scenes. That actually this here transforms actually into something like do parser monad. This actually transforms into actually using a monad. And right now we're seeing, you know, before we have always seen this vector tuple have nothing inside of it, be always empty, and right now we're seeing it with content. Well, that's, you know, in monads you can create variables and bind them to monadic operations, and that's actually what we're doing here. We're creating this variable. It comes from the output of this here, this variable here gets its value from the output of this monadic operation, and so on and so forth. We're going to be exploring more of that in future videos, but right now let's just say that we are using monads undercover. So you are a monad programmer, even if you don't know it. So, now we have our values, right? So let's do something with them. Let's generate our code, right? Let's generate our code. So let's see. By the way, the code inside the def syntax is also within the looks monad. So we can just wrap something without having to do something like do looks monad before. We don't need to do this. I mean, we can if we want to, but we don't need to. We can just wrap it directly, and that work is done for us. It's great for many simple macros where you don't really want to waste your time entering the monad. So we're going to be generating some code. Remember, a list of code, because macros generate lists of outputs. And we're going to be referring to this. Well, we're going to be using the unhygienic part. So we're going to be using looksDef, which is the default, the primitive way of making definitions in looks. Well, actually, we shouldn't be making the code immediately. We need to actually pattern match against this to know what we're doing, right? Oops. So we got this declaration, and if it's a simple name, then this is what we're gonna generate. And by the way, I'm gonna be introducing another module. It's called AST. It contains functions for generating AST nodes based on values. Like, for instance, name is not an AST node. It is text. So we need to transform it into an AST for our templating purposes. So we're going to be using the function symbol from this module. We give it an empty prefix because we don't care, and the name of the definition we got. Then we put the type, and then we put the value. Simple as that. The simplest way to make a definition. And for the case of making a function, then we're gonna make it so that here we have the name, here we have the type, and here we're gonna be piggybacking on lambda, splicing the arguments, and putting the name here in the lambda too, in case our function happens to be recursive, as is the case, for instance, in factorial. So we have the name on the definition, and we have the name of the function itself for the sake of recursion. So we're piggybacking on other macros, but that's a pretty normal thing. Macros tend to be written in terms of other macros very often. So now we have our own way of doing these definitions. Really nice, huh? Really cool. Now, you might ask yourself, why am I using this version of the templating macro instead of the version that we saw most yesterday? And the reason is that this one is hygienic and this one isn't. And what's going to happen is that this one, which is hygienic, is going to look at this and it's going to be like, okay, does there exist a definition somewhere in my module or in my imports named looksDef? And the answer to that is false, because looksDef is not a definition. It is a special form. A special form is a name given to special constructs in a Lisp language. So since this is a special form, this macro, which doesn't recognize it, is going to complain. It's going to be like, hey, I don't know this symbol. What the hell are you doing? And we're going to get an error. Now, if I give it a prefix, it's not going to complain, because it's going to be like, okay, I don't know the symbol, but you're giving it a prefix, so I assume you know where it comes from. And the beautiful thing about special forms is that you can give it any prefix you want, and the compiler is going to recognize them anyway, because the compiler really doesn't care. It doesn't examine the prefix, it only examines the name of the form. But it will be kind of annoying having to put those fake prefixes everywhere. So I just use the unhygienic templating macro to save myself the trouble. So let's see if our def macro indeed works. Let's see. So we're gonna be compiling again. Oops, looks like something went wrong. But what did? Can't redefine program assert. Oh, right. Yeah, I'm getting it from CLI. Doesn't matter. Yeah, sorry. There is another assert parser coming from another module, and they collided from the one coming from the syntax module. Oh man, even more stuff. Oh, yeah, right. I forgot. There's quite a lot of combinators in it. You know what? Screw it. Just import it this way. I'm not using it directly anyway. Let's compile this down. Hopefully, you know, third time's the charm. No, it isn't. Oh man, what now? Yeah, I'm sorry for doing this debugging. I didn't run this code previously. Oh! Ha ha! It comes because we're trying to use the common macro that we have not yet defined. But hopefully, you know, this convinces you that we are using this common macro that we defined in the previous episode instead of the one from the standard library. So you're not gonna think that I'm a liar or anything like that. Since there was a problem here, what was it? Ha ha! Man, this is just crazy. I'm trying to use def from the standard library, but of course we did not import it, so I cannot use it. You know what? Fine, doesn't matter. Let's do things the primitive way. There you go. I'm sorry if it looks kind of funky, but we're gonna be doing things with this. I mean, we could use the def from the standard library by just prefixing it, but nah, didn't go for that. What now? Looks unknown syntax looks def. Well, that is funny. That is funny. So that is real funny, actually. Oh, I'm sorry. Now I know why it's complaining. Let's just say that LooksDef expects a little bit more information than what we're passing right now. So you know what? I'm not gonna deal with that hassle. It's just, you know, LooksDef as it is actually expects extra information because it expects some metadata that I didn't give it, but that is not a subject for today. So fine, I'm gonna use a prefixed version from the standard library. Sorry for the debugging, but hopefully this is actually teaching you some things about how looks works. Oh, we actually got to compile even this stuff. So why didn't this compile? Oh, I know why it did not compile, because I haven't put some metadata here either. Oh man, where is the metadata supposed to be? Name. Oh, meta over here. Fine. Whatever. Let's do things the hard way. Yeah, sorry about this. I haven't been using the direct form of LooksDef in a while, as you can imagine. See if this one compiles. Please. Oh, finally. I've got it. Okay, this place here where I put the list, this is where the metadata is supposed to go. Anyway, it finally compiles. Let's run this. finally it works. So, we have gotten a little taste of how to use syntax parsers to do some complex parsing of our inputs to macros. And this is still a very like simplistic example. You can get really funky with this thing. Like in the standard library, I have some examples for parsing some macros for making classes and stuff. Like check this out. Like this JVM import stuff, and like oh man, like parsing all kinds of macros, class declarations, some member declarations for the classes that you're importing, and some tag serves as a kind of boolean flag, and I have this some more complex macro. Oh, check this out, man. Way to define classes. This is a really complex macro. Sorry. All of this is actually just example code. It's not part of the definition. This is just something for documentation. So forget about all this. Forget about this. So you see the definition is actually much shorter. So I'm sorry if that scared you. But check this out. Check this out. It's incredible. Inheritance modifier, class declaration, superclasses, interfaces, annotations, fields, methods. A lot of stuff in here. Ton of stuff. Defining interfaces, defining anonymous classes. This is just madness. You can go really crazy with your parsing. And if you checked out this module, I have like, okay, these are all data types for things that I'm parsing. Let's see. There's some generators. Where are the parsers? Oh, here are the parsers. It starts in line 612. Up to where do we go? We go. It's insane. It's 400 lines of parsers. Some of them fairly complex, like this one. You can go really crazy with your parsers and make incredibly powerful macros that work with incredibly powerful and complex code. And you can do it in very easy ways. I mean, way easier than doing pattern matching, and way easier than pretty much other Lisps. I mean, I'm not trying to throw shade at anybody, but if you have ever written a complex macro in Clojure or Common Lisp, it might not have been a pleasant experience. And it's precisely because it lacks tools like these ones that allow you to make really complex macros out of very small and simple parts. Most importantly, they can be combined. Oh, and by the way, here I have some examples of using the parser monad directly instead of just using the combinators. As you can see, you can do it. It's mostly useful for when you're trying to, maybe generate data structures whose structure does not match the way you're parsing things directly, so you might want to shift things around or maybe apply some function somewhere. So the parser monad, direct use of the parser monad has its place. So this is all for today. This is what I wanted to talk to you guys about. Syntax parsing is amazing. You have no idea. I mean, again, this is just a very simplified example, but I've written some pretty crazy macros that I am not sure I would have been able to write with the same level of quality or power, much less complexity, in Clojure. I wouldn't have been able to do it. It would have been just too annoying, too hard. But with this, piece of cake. So, yes, that's it for today. And for tomorrow, what's there for tomorrow? We're gonna talk about advanced macros, advanced pattern matching. Finally, you're gonna see some really crazy applications of macros in Lux that you don't find in other Lisps. It's gonna be awesome. And I think we're also gonna talk about I/O and working with command line interfaces. So that's it for today, and I hope you enjoyed this episode. I sure know I did. Talk to you tomorrow.